On September 17th, 2025, a home telescope in Austria captured faint spots of light moving past the stars. Tom Slayman had been observing this object for several weeks. It was divided into three parts, as if it were an interstellar comet. She came from beyond our solar system, flying at a speed of 60 kilometers per second. Something changed this evening. The comet suddenly flared green. Not over hours, but in mere minutes. Tom watched the screen, observing a surge of brightness. A blurred glow around the core intensified, as if someone turned on a light at a cosmic level. He checked his equipment. No errors. The comet was indeed exploding with light. In a few hours, two experienced comet photographers in Namibia, Michael Yorber and Gerald Trayman, aimed their telescopes at the same target. They had a total of 10 years of experience. They had seen thousands of comets, but what appeared in their photographs stopped them. The comets not only grew brighter, their coma glowed with a terrifying emerald green. There was another detail, a curve, a ripple, moving along the tail like a wave on water. It was exactly what the title promised. An amateur astronomer had just captured an interstellar visitor doing what it shouldn't be doing. Something that challenged the slow and predictable behavior we expect from comets. Perhaps the three parts of the comet just switched modes in real time. Did some internal trigger activate? A powerful outburst of gas and dust occurred. The green color tells part of the story. This is a diatomic carbon, a molecule that glows green when excited by sunlight. Each comet carries something with it, but so much and so fast. It's unusual, and this bend in the tail suggests that something has penetrated through the comet's gas cloud, something external. This is exactly what causes concern. Just a few days ago, there was an eruption on the sun. A coronal mass ejection detached from the surface of our star, and magnetic plasma burst outwards at millions of kilometers per hour. Space meteorologists calculated that the trajectory pointed directly at three divided parts of a comet. The collision was predicted for the 24th or 25th of September. The timing matched. A green flash, a twisted tail, a sudden burst of brightness. All of this happened just when a solar storm was about to collide with a comet. For the first time in history, we might witness our sun colliding with a visitor from another star. And an amateur astronomer captured the moment it happened. So what exactly did these telescopes capture? Let's break it down without delving into technical details. The brightness curve tells the first part of the story. The brightness curve is a graph showing brightness over time. When you plot a segmented graph, that night you will not see random flickering or noise. You will see a clear, coherent rise. The brightness of the comet increased with a smooth surge. This indicates that something real happened, something physical both inside and around the comet. The change in color is the second sign. The coma begins to glow a bright green, and then over the next few hours, it partially calms down. It does not return to its previous state but becomes less bright. This cannot be an equipment error, as three different observers on two continents are recording the same phenomenon. Identical time intervals, the same green hue, the same brightness jump. Then a tail appears, and consecutive frames show changes in its geometry. The tail is not static. It bends and twists as if something has passed through it, leaving it in an excited state. Frame by frame, one can trace the waves of disturbance spreading from the core. When news of this begins to spread among comet observers, both professional and amateur, they quickly respond. They extract archival data and check other telescopes that might have recorded this event. Everyone confirms their observations. This was not a camera error. It was happening for real. The green glow is key to understanding what is happening from a chemical perspective. The green color in a comet almost always indicates the presence of dicarbon. When ultraviolet light from the sun hits these molecules, they absorb energy and emit light in the form of green light. This is the same process that makes neon signs glow. Thus, this green flash indicates that the comet suddenly released a huge amount of carbon molecules into space. Now a complex question arises. Why did this happen at that moment? Three explanations come to the forefront, each testable and suggesting different details. The first explanation, a new source has opened. Comets are not smooth. Their surface is bumpy, cratered, and cracked. It resembles a patchwork quilt made of various materials. Some areas are covered with a hard crust formed over billions of years by cosmic radiation. Beneath it lies untouched material. As the comet approaches the sun, heat penetrates inside. Eventually, a weak spot cannot withstand it and cracks. A fresh layer of ice is exposed to sunlight for the first time in centuries. It instantly evaporates, and gas and dust burst out. This could explain the sudden burst of brightness and the green glow. The second explanation, a solar shock wave struck the comet. Remember that coronal mass ejection the sun produced a few days ago? It's not just particles. It's a compressed bubble of magnetic field and plasma. When he encounters the coma of the comet, he compresses the gas, heats it, and can even tear parts of the tail. Think of it this way. A coronal mass ejection is like a sudden gust of wind. The tail of the comet can be compared to a flag in the wind. When the gust intensifies, the flag tears and twists. This bend in the tail may be a sign of impact. The third explanation, the comet's nucleus is rotating. Most comets rotate, some smoothly, others chaotically. If the three parts of the comet, separated by a tail, tumble, different sides of its nucleus face the sun at different times. Perhaps one side of the comet is darker and absorbs more heat. When it turns towards the sunlight, its activity increases, and the comet becomes brighter. Then, when it turns away, everything calms down. This leads to periodic bursts related to its rotation speed. Each hypothesis creates specific predictions. New openings in the core should maintain increased brightness for several days or weeks. The solar shock effect should be short-lived, possibly lasting only a few hours. When rotating, the flash should repeat on a predictable schedule. Here, condensed photometry comes to the rescue. It's just a complex term for many measurements over a long time. If you measure the brightness of a comet every few minutes or hours, patterns can be revealed. Does it flare up once and remain bright? Or does it suddenly intensify and quickly fade? Does this repeat like a lighthouse signal? The data will indicate which hypothesis fits. But what distinguishes this case from all other comet flashes we have studied is that it is not a comet from our solar system. This is a stranger. It formed around another star and traveled through interstellar space for millions or billions of years. Its chemical composition may not match anything we have seen before, and now we observe how it reacts to the brightness of our sun in real time. Why is this important? This goes beyond a beautiful picture on a computer screen. Interstellar comets are samples, physical parts of other solar systems, delivered right to our doorstep. Every molecule, every speck, every chemical signature comes from a place we can never visit, a star barely visible to us, a planetary disk formed 7 billion years ago. When the comet 3A Vaidet-Biatlos suddenly ignites, something important happens. It reveals an outer layer that has been bombarded by cosmic rays for centuries. The layer deflates, and fresh material beneath it sees sunlight for the first time. This fresh material carries the original chemistry of the place where the comet formed. We can analyze substances that have not changed since its birth. This rapid change allows us to explore a composition that was previously inaccessible. Before the comet's flare, 3 A's and 2 D's in Vaidet-Biatlos appeared relatively calm. Its spectrum showed some gases, but not others. After the flare, new molecules emerge, different ratios, different colors. It looks like a slide and deslide. Only the comet does it for us. Time here decides everything. Right now, 3 A's, separated by a gap, are still bright enough to be studied with medium-sized telescopes. In a few weeks, it will dim as it moves away from the sun. Next year, it will disappear forever, soaring back into interstellar space. This window is closing, and every observation matters. This is where astronomers and enthusiasts become indispensable. Large telescopes like Hubble or James Webb operate on a tight schedule. They can dedicate several hours to one goal and then switch to something else. Unlike them, hobbyists with their own equipment can observe every night, filling in the gaps. When something unexpected happens between scheduled professional observations, it is the amateurs who notice it. This is what happened in this case. Without Thomas Lehmann's telescope, we could have completely missed this flare. But there is another important aspect that raises the stakes: mass. Before we continue, consider the following question. What do you think caused this surge? Was it a hole opened by internal pressure, or a solar shockwave striking the comet from the outside? Share your theories in the comments, and then keep an eye on the news, as the current best matches may surprise you. If you are interested in such data analysis, where we let facts shape the story, don't forget to subscribe. This really helps us keep you updated. Now let's return to the question of mass. Everything changes when astronomers first calculated the comet's trajectory and noticed something strange. The orbit showed almost no gravitational drift. Let me explain what this means. Most comets do not move along perfect trajectories dictated by gravity. When they emit gas, these jets act like tiny engines, slightly steering the comet off course. Over weeks and months, this creates a measurable deviation. The comet is in a slightly different position than pure gravity would predict. Strong streams lead to large deviations, while weak ones result in small ones. In the case of this comet, there is almost no deviation observed. It moves almost exactly along the trajectory determined only by gravity. This tells us something important. Either the jets are perfectly balanced and pushing in all directions, neutralizing each other, or the core is so massive that the jets cannot move it. It's like trying to push a cargo ship with a handheld fan. The ship is too heavy to notice. The data points to the second option. Researchers led by Avi Loeb from Harvard calculated the figures. For the jets to have such a negligible impact, the core must be at least 5 kilometers in diameter and possibly more, with a mass exceeding 33 billion tons. This is orders of magnitude larger than the previous interstellar objects. ʻOumuamua was possibly only a few hundred meters long, and Borisov's core was less than a kilometer. This object eclipses them both. Houston, we have a problem. I don't think this is Florida. Fortunately, I didn't need NASA. I needed a real team. There's a law firm called Morgan & Morgan, the largest in the United States, with over 1,000 lawyers and offices across the country. I tried to call one of those local offices, but the wait on the line was much longer than the delay of a spaceship launch to Mars. Meanwhile, Morgan & Morgan helped their client in Florida secure $12 million when the insurance company offered only $350,000. This firm charges only if they win the case, with no upfront payments required. You can file a lawsuit without getting off the couch or even while in the jungle. It's that simple. Just click the link in the description or scan the QR code on the screen. If you ever get injured, contact Morgan & Morgan. Their fee is not charged if they don't win your case. You can start filing a lawsuit simply by clicking the link below or scanning the QR code. Now about the comet. When a bright comet suddenly appears, it may indicate active processes within. The mass of a comet may hide complex structures, such as thick crusts and pockets of volatile ice, which are not visible from the outside. If a comet suddenly becomes 40 times brighter in a month, it is certainly not just a dust shell. This indicates deeper processes. If a comet emits gas, it can affect its trajectory, but if it remains steady, it is either heavy or the gas stream neutralizes changes. When we observe a sharp increase in brightness of such a large object, it attracts attention. Perhaps something inside could crack, even if only for a moment. What lies within has not seen light or interstellar space for a very long time, possibly billions of years. And this is where the most interesting part begins. Most theories suggest one reason. Either a gas pocket opened up or a solar shock wave affected the comet. But what if both factors are influencing simultaneously? A two-step model might better explain the timeline of events. First, the gas pocket is activated, followed by a solar shock wave. Consider the sequence. A few days before the flare, the comet begins to heat up as it approaches the sun. The internal pressure builds beneath the surface, and a weak point cannot withstand it. Fresh gas evaporates, and gas begins to be released. This is the first stage. The comet becomes brighter, its coma glowing green. Then a solar shock wave arrives, crashing into the already active coma, compressing the gas cloud and creating fractures that observers record. The second stage occurs simultaneously with the first. The order of events matters. First, the fatness appears, then the shock wave. This helps explain both the green flash and the change in the comet's tail shape. This is something enthusiastic astronomy lovers can verify. Polarimetry is a method where light, reflecting off dust particles, becomes polarized. The degree of polarization depends on the size and composition of these particles, and this can be measured using available filters that can be attached to a telescope. Expensive equipment is not necessary. Unusual polarization could indicate that the particles are larger or darker than typical comet dust, confirming the hypothesis of a solid crust. Cosmic rays impacting the surface of a comet for billions of years could have fused dust particles, forming larger and darker particles. When these particles are finally expelled during an eruption, they appear differently in polarized light. Imagine, the rising sun illuminates a frozen lake. The ice cracks from thermal stress, mist rises, then the wind blows over the lake, creating patterns. First, a crack appears, then the wind. Both factors are necessary to explain what you see. Viewers were interested in the green color in previous videos. The green color usually indicates diatomic carbon, which glows under sunlight. Thus, the green flash indicates the presence of fresh gas, not just dust. That's why this moment is important. This is chemistry, not just a visual effect. We observe how molecules formed around another star react to our sun for the first time in billions of years. Now about synchronization. Spacecraft operating near Mars can provide side views into this window of time. The NASA Mars Orbiter and the European Trace Gas Orbiter were set to observe the phenomenon from different angles, separated by distance, around October 2nd. just a few days after a flare occurred during a close approach to Mars on October 3rd. The second observation point changes everything. From Earth, we see one angle. From Mars's orbit, another. Together, this data constrains the geometry of the jet. They show where the active regions of the core are and how the hypersonic tail spreads in 3 dimensions. Solar probes can independently record the arrival time of shock waves. The Parker, Solar, Probe, and Solar devices measure solar winds and track coronal mass ejections as they expand. If they had recorded data about this specific coronal mass ejection, we could synchronize enthusiasts' timestamps with plasma data. We would know exactly when the shock wave reached the comet. The study becomes measurable and predictable. Mature observers see optical changes at specific times, while solar probes record when the shock wave has passed. The Martian device observes the geometry from another angle. Together, all 3 datasets would capture a 2-stage model. No conjectures are needed, only geometry and time. Polygonal comparison would become irrefutable evidence. It will confirm that we are not looking for coincidences. We are analyzing the actual sequence of events determined by predictable physical processes. This led to the formulation of a theory. Perhaps the core is a contact binary star, where 2 stars merge while rotating. One heats up faster than the other. Channels open unevenly, creating periodic brightness bursts associated with the rotation. There is also another theory that a rich layer of carbon dioxide has just opened up. Carbon dioxide evaporates at lower temperatures compared to water vapor. If the sun's heat finally reaches the pocket of carbon dioxide, it will begin to sublimate violently. This may explain the intense green glow. The decay of carbon dioxide releases carbon, which in turn explains the rapid dimming. Once a pocket breaks through, activity decreases until the next pocket opens. Both theories predict recurring bursts of brightness. If the comet makes orbits, the bursts should occur on schedule. Each orbit returns the active side to its manifestation. If these are layered pockets, the bursts will happen irregularly. The absence of repeating patterns weakens the idea of a tumble. Random bursts support the pocket model. Multiple bursts at regular intervals confirm the rotation. The data will help determine which theory is correct. We can verify this together using a 10-minute rhythm and the same filters over several nights. If the splashes occur on schedule, the likelihood of a tumble decreases. If the splashes happen only after sunstrokes, the cause will be the sun. In any case, we learn quickly, and the necessary equipment is already available in many observatories. The significance of citizen science becomes clear.